One of the first things that we were able to do before the trip known as the Little Rock Express, we were actually going to use the Challenger, the 3985. That was going to be the locomotive that we were going to use that year, and I had wanted to take our time and really proceed with some upgrades that we were working on with this locomotive. It had new crank pins applied, first time probably since the 50s. And a crank pin on a big engine of this size is a big job. You know, it's a special metallurgy. It's not to be taken lightly. The pins themselves are pressed in with well over 100 tons, nearly 200 tons in the case of the mains. So it requires a lot of capability. So finding a place that can make that forging for you with that correct alloy, that's going to take some lead time. Finding a reputable machine shop that's got the capabilities to handle that type of heavy work, that's something else that has to be handled. So we had all of that done, and the wheels arrived back here. Now it was time to go through the side rods. These side rods were built roughly in 1952 by Baldwin Lima Hamilton. They had a big hammer, and Alco contracted that work out. They're the newer design, they're lighter weight alloy, and they were projected, all the superpower was projected to run into the 1960s, roughly. Well, how long ago was that? I was born in the 1960s. So this locomotive has seen service well beyond its engineered life. And the way it was designed in such a way, and forgive me if I'm overly technical about some of this stuff, but the side rods do not have a bushing inside them. On the number 1 and the number 4, for example, the bearing runs on the actual rod. In 1944, that wasn't a big deal because the rods were nice and thick, had a big heavy cross section, and throughout all the various shoppings, every time the locomotive is shopped, you restore all those dimensions to the correct orientation, and it's all restored and shopped and it's placed back in service. And even with all those multiple shoppings, you will never get to the point to where you thin the cross section to the point to where the rod's no longer safe. That's where we are today. So for those on the internet, they never run 70 anymore, they don't. Well, there's a reason why. When we went through, we are at the last of our side rods. We had a small supply from the 838, and over the years they've mixed and matched. A few years ago, 10, 11 years ago, the locomotive derailed on the Y in Denver, and that bent one of the connecting rods in the front, which took that rod out of service, so there went one. So we had to take another one. Had an engineering company come up and conduct a very comprehensive engineering analysis on the fitness of the rods. They x-rayed them, and they did a wet mag particle test, and that certified to me that the rods were safe to continue to be used. So once we determined that the rods were safe, now we had to mix and match and put them all together again. So myself and some of our staff, we went to a machine shop in Denver, and we figured we were going to be there 3 weeks. We were there 5, and we enjoyed a very good working relationship with the shop because we effectively came in, and usually when you take something to a shop, you give it to them, you tell them what you want, you give them some drawings, and they call you when it's done, and you come pick it up. We were there every day, and we met with them, and we were actually on the shop floor guiding and helping and being a part of that operation. And here's why. Because remember I was telling you how the rods were thinned year after year? So we had to be very, very diligent and careful and analyze how much we had to take off to restore that 88-inch dimension, which is known as your tram, between each rod center. The unique thing about a modern superpower locomotive, these rods are what they call articulated or knuckleless rods. They're one big piece. Not like a narrow gauge locomotive where you can drop a knuckle pin and out comes one rod, and the guy, I remember when I worked in Durango, you could take those rods apart by one guy. This requires a special fixture that we made to get that entire unit on and off again. And you have to disassemble them by pressing bearings or bushings. The slang term is known as a gunnister bushing. The technical term is a knuckle bushing, and that's where the fork in the eye of the rods, again, forgive me for being overly technical, but the rods are assembled together, and that they knuckle or they move, and that allows the locomotive to go over differences in elevation, cross elevation, and vertical differences in the track. Well, all those dimensions have to be very precisely machined because they're placed back together with interference fits. So we made all new knuckle bushings and all new fittings for the rods and all of that. So with that in mind, we had to literally be like a mother hen in that machine shop and make sure they did not take any more than we absolutely had to. There were some days we, again, because of the wonderful support that we see in this department, we bought a very expensive measuring device known as a ferroarm. And it's a high-tech device originally used in the medical industry to measure bones so they could make prosthetic limbs. Well, it's been adapted for general use, and it's a wonderful device for those that know how to use it. I will admit to you, I'm in my 40s. I'm not that much of a computer guy, but our young staff, they picked it up like they've been running the thing their whole life. So we brought that with us, and we were able to achieve 4 decimal point accuracy, which is well beyond what I wanted. I have a sickness known as perfectionism, and you got to be careful on a steam locomotive because a steam locomotive is a big machine that requires clearances to operate. But I told the machine shop I wanted very, very close, accurate work because we don't have the room. We can't afford an error. So having said all that, we're able to get everything back together. We used liquid nitrogen. We made fixtures and set everything up in such a way to where we could freeze the metal parts that have to be pressed with an interference fit. I did not want, nor could we afford, any error. And whenever you're pressing metal parts together, even in a very accurate setting with good, accurate hydraulic presses and so forth, there's always a chance that those parts that are being pressed together with an interference fit, which means that one component is made larger than another component. The metal has to move to accommodate those pieces coming together, and it's all engineered. We could not afford to mess these rods up. And you're pressing them together with 2 parts here, pressing another one here, and you're putting a bushing in between. And there's all these different fits that fit in there. So we use liquid nitrogen. And it took several days to get it set up and measuring and checking and measuring. And we got it all set up and it went together just beautifully. I had goosebumps telling you about it. I mean, it was a little harrowing because of what we were dealing with. In addition to that, we had to leave on this trip in a few weeks. And we don't have a break-in. We don't have a break-in opportunity. I don't have a treadmill I can put this thing on. So when this thing goes together, it's got to go together right the first time, and we can't get it out there and burn the thing up or tear the thing apart. So it was an interesting time. Pardon me?
Where did you have the work done in Denver?
When?
Where?
Denver Machine Shop. Denver Machine. Great group of guys.
Well, right.
They're down by not too far from Coors Field. Yep. Yeah, they were real patient with us. Like I said, it's not often that a machine shop will let you take over, come in and tolerate you. No, we need to do this. There were days that we were only able to get 1 rod done because over the years the rods get a little tweaked here and there. They're polished and they get rusty and they're polished again, and the surfaces become irregular. So when you go to set that up and you start to dial that component up, it's hard to find a regular surface, so you've got to start mixing and matching and splitting the difference, and we just could not afford. We were taking 6 and 7 thousandths off, and that was enough to clean up the circumference of the fit, and we had to split the difference with the other bore. We just couldn't arbitrarily plunge here, zero that, and then go 88 inches over and plunge here. We didn't have the metal to work with, so it was really touch and go. But we made it through that. We brought them up here, and then we had to put the rods up. And a roller bearing engine has to be lined up correctly, or those big flanges are going to eat themselves up. So we went through a process. Again, I'm a person that likes the old practices. I love technology and I like to use it where it's applicable, but there's some times when you just got to do it the old-fashioned way. We used the Faro arm, and we were able to start at the front of the locomotive and triangulate all of these dimensions with this device, literally walking itself around the locomotive, so we could determine all the right relationships, and from there add shims where necessary, so we've got those axle centers exactly 88 inches. Once we did that, we made a big special fixture, a huge I-beam, giant I-beam, with independent ability to adjust each rod, and it goes up with a forklift and we can put the rods up as one unit. Once we did that, and this took several days, we put a set of rods up, and then we put the other set of rods on the other side, and then we gave it the test, where we'd bring the locomotive, when we put the rods, what's called top quarter, right on the very top in the 12 o'clock position, and take feeler gauges, and then run those feeler gauges around each bushing, and make sure we've got uniform clearance where we need it. And then we'd move it to the front quarter, which is the 9 o'clock position. We'd do the same thing. Well, we went through all those tests to verify that all of our machining was correct, all our measuring was correct, because like I said, once we take off out of here, that dispatcher's not going to look too kindly on me if we're out there having trouble or running slow. So we did all that. The next test was we were going to see how the locomotive rolled, because I wanted to see if anything bound. So we started to move the locomotive, and we'd move the rods as it was moving to make sure nothing was binding, because that's an indication we've got a problem somewhere. Passed all those tests, we put it together, we took off, and here we are. This locomotive experienced a significant problem in 1999, and it started to undergo a major rebuild, in which the firebox, combustion chamber, and front and rear tube sheets were replaced. And as the project developed, there was a decision made that they would not replace the bottom portion known as the mud ring. Well, it's time for that to happen now. The area is thin, wasted, and it's been leaking. So what we've done on both sides, we've gone in and removed that part. And everybody kind of walk around, be really careful. Let me make sure they're not going to do any grinding. Anybody up here? Okay, all right. Come on over here, everybody, and have a look in here. Let me explain what we're doing. We removed all of the refractory, all the fire brick. One of the interesting things about boiler work is it's very difficult work. And it's uncommon in today's world to do significant boiler work on a big engine. Durango and Silverton, a lot of the railroads, they do boiler work frequently. It's just a matter of part of the daily work scope. We've got to drive almost 200 rivets, these big special rivets that fit through here, to get this repair completed. Yeah, really. When we started this back when we came in after our historic trip last year, I was talking to the foreman and talking to some of our staff, and I said, let's just get our heads around this from the beginning. Because typically when you get into boiler repair, you'll pull a little fire brick here and you'll look at it and you'll UT it. Well, you'll find a problem, then you'll pull some more fire brick out and you'll UT it some more, and then you just kind of piecemeal your way around it. Well, my thinking was from the beginning, let's not get discouraged in our thinking about having to continue to get deeper and deeper into this. We're going to disassemble it completely and get in there to where we can get a good look at it, evaluate it, and whatever needs to be fixed will be repaired. So we've got the fire pan completely removed, as you can see. And now if you look up underneath, you can see on the other side, that is the new patch. And you can even see this is called the wrapper sheet. On the inside is the firebox. Now there's refractory up a few rows of stay bolts. The fuel that we burn approaches 2,000 degrees in temperature. And when you consider this is a 5,000 horsepower power plant on wheels, you've got to burn 5,000 horsepower worth of fuel. And that heat is transferred through those sheets. and that water is 425 degrees at 300 psi. So you can understand the degree of work that's going to go into maintaining a pressure vessel like this.
Yeah, what was the temperature?
425. And that's the saturated steam temperature in here. Once it goes through the superheaters, we're pushing 700. So for those of you that want, you're welcome to come have a look in here.